A tire is not a solid rubber ring. It is a composite of hardened rubber, steel wire, steel belts, and reinforcing fabric, all bonded together to resist everything the road throws at it. Turning that into clean powder for a new highway takes machines most drivers have never heard of. Keep watching for the racing surface flat enough to shock you. A mining truck tire can be so enormous that even moving one requires specialized equipment built around their size, and one region of Western Australia throws away 50,000 tons of them every year. Until recently, almost all of that went into landfill. A new plant in Port Hedland now handles 30,000 tons of those giants annually, resizing them on site before shipping the material south for further processing into crumb rubber that ends up in state road surfaces. Which raises the obvious question, how does anyone break something built to survive 400-ton loads? Getting a 57-inch tire from a bauxite mine to the recycling floor is a logistics puzzle before it is anything else. Flatbed trucks with oversized permits haul them stacked too high, strapped down with red ratchet lines. Later stops turn those same giants into fine black powder for road surfaces, athletics tracks, and playgrounds. Before any factory can run, someone has to actually collect the tires, and that turns out to be the hardest part nobody films. A new collection truck design cuts loading time from an hour to about 30 minutes per stop, handles roughly 60 to 70 tires per pickup, and drastically reduces the lifting workers have to do by hand. Multiply that by every gas station, mining site, and city depot across a country, and the scattered rubber starts adding up fast. A regional collector in central France runs pickup across 8 departments, hauls the tires to a consolidation yard, and unloads them onto sorting piles that quickly grow into mountains. Here is where most people underestimate the industry. The recycling itself is only step 3. Steps 1 and 2 are logistics and sorting, and both cost more than you would guess. Telehandlers move stacks, trucks reverse into loading bays, shredders start reducing the piles into either fuel chips or aggregate for civil works. Once that scattered supply funnels into a real processing plant, the scale jumps by an order of magnitude. A facility in Germany takes in around 400,000 tons of end-of-life tires per year across its network, with one plant alone recycling 25,000 tires every 24 hours, running around the clock. 25,000 tires a day out of one plant? That is the pace this problem actually operates at. And every ton recycled instead of incinerated saves at least 1.1 tons of CO2 emissions. And plants at this scale are the reason the tire problem is even solvable. One Australian facility processes almost 20 million tires per year, backed by more than $10 million in specialized equipment on the site alone. A lot of countries still export baled tires overseas to avoid dealing with them at home. Should governments require domestic processing capacity for every ton their citizens generate? Or is offshoring fine as long as the receiving country has real recycling infrastructure? The volumes here matter because Australia historically exported around 60,000 to 70,000 tons of whole baled tires offshore, often to poor environmental outcomes. Domestic capacity finally closes that loophole. Behind every finished bag of black powder sits a national network most drivers never see. Dedicated collection vehicles, secure processing sites, specialized shredders, and granulators, all feeding rubber crumb into fuel recovery, playground surfaces, sports fields, road paving, and tile adhesives. But collecting the tires and destroying them are two very different problems. And here is where the actual destruction begins. A tire is not a solid rubber ring. It is a composite of vulcanized rubber, steel bead wire, steel belts, and reinforcing fabric, all bonded together specifically to survive impacts, punctures, and 100,000 miles of road abuse. A giant primary shredder feeds whole tires between 2 counter-rotating shafts with heavy steel hooks that grab, tear, and pull the tire apart layer by layer. The output at this stage is not clean rubber. It is rough strips, maybe 6 to 12 inches long, with steel and fabric still visible sticking out of every piece. Once the tire is opened up, the next machine gets pickier about size. A dual-speed chipping shredder runs at 2 different speeds depending on what enters the hopper: 22 revolutions per minute for passenger and SUV tires, 11 revolutions per minute for the heavier semi-truck tires up to 22.5 inches on the rim. Output runs 8 to 12 tons per hour, which translates to about 1,000 passenger tires or up to 200 truck tires every 60 minutes in one pass. The trick is a patented internal screen combined with a recirculation drum. Properly sized chips fall through and exit the system. Oversized pieces get pulled back to the shredder for another pass. The screen itself can be swapped to change output size: rough shred for landfill, 4 to 6 inch chips for civil engineering aggregate, or 2-inch chips for tire-derived fuel. No wasted passes and no oversized chunks slipping through downstream to cause problems. Which is why one Australian operator scaled from 200,000 tires per year to 200,000 tires per month after switching machines. The key advantage he mentioned was durability plus one design choice most viewers would overlook. The shredder exposes the internal steel wire early, so magnetic separators downstream pull it out cleanly instead of chewing up the rest of the line. That change cut his wear parts bill by roughly 40%, because the steel was leaving before it could grind down blades meant for rubber. Put those individual machines end to end, and a full recycling line starts to look less like a factory and more like a conveyor river. A complete Swedish tire processing plant chains together primary shredding, secondary size reduction, steel separation, fiber removal, and final screening into one continuous flow. Whole tires enter one end. Sorted streams of clean rubber granulate, recovered steel, and separated textile fiber exit the other end, each going to a different market. But turning a chip into something useful is not the same as turning it into something clean. Because rubber that looks clean and rubber that actually is clean are two very different products. A full 4-stage Crumb rubber system walks through the whole logic in order. Stage 1 takes whole tires down to rough chips through multiple passes and a classifier that sends oversized pieces back for another cut. Properly sized chips can already be sold as fuel to cement kilns, paper mills, and power plants, where they replace coal at meaningful cost savings. Stage 2 is the make-or-break step, separating steel from rubber cleanly. Pre-shredded chips, 4 to 6 inches in size, enter a machine that rips the steel out. A belt magnet lifts the freed wire away. Then, a secondary vibrating screen and drum magnet catches any steel still riding on rubber and sends it back around, which is exactly the kind of loop that separates a modern plant from an amateur operation. Nothing worth recovering gets thrown away, and everything gets a second chance to end up on the correct side of the belt. The star of this stage has a name: the Liberator. A patented, serrated knife design and an armor-plated rotor rip the internal wire out of tire chips efficiently enough to produce rubber up to 98% steel-free. The recovered steel is the unsung hero of a good tire recycling plant. Cleaner it comes out, the more scrap dealers pay for it, sometimes dramatically more per ton. And here is where a lot of recyclers leave money on the table. Steel wire coming out of the Liberator still carries rubber and fiber contamination, and scrap dealers heavily discount dirty steel because they have to clean it themselves before it can go into a furnace. A standalone wire cleaning system uses mechanical separation and vibration to strip the last rubber and fiber off the steel. Cleaned wire commands substantially higher resale prices. The economics quietly flip. Steel goes from a low-value byproduct to a real second revenue stream that changes the math on the whole operation. By stage 4, the material is unrecognizable as anything that once rolled down a highway. Rubber granulate gets fed into a dual-drive cracker mill, 2 serrated hardened rolls positioned very close together that crack the granulate down to fine powder ranging from 20 to 80 mesh. Because friction generates heat, a chiller keeps the machine cool. A gyrating screen system sieves the powder into precisely different sizes. Now the question shifts from destruction to reuse. where does all this black powder actually end up? And here is the payoff the video promised in the opening. A mining tire and a road surface finally in the same shot. Bags of Crumb rubber pull up next to a mobile mixing plant. Operators dial in binder ratios, hook up hoses, and a truck starts spraying the blended surface onto the road. But pull the cover off any asphalt plant, and the operation is far more finicky than it looks from the road. Different sizes of rock and sand, called aggregate, get pulled from separate cold feed bins by variable speed conveyors, each proportioned exactly according to the mix formula. A rotary dryer with an embedded burner heats and dries every particle over 3 to 5 minutes because the liquid asphalt binder cannot bond properly to wet aggregate. 50 to 60 miles per hour inside the dryer. That is how fast the gas moves when water flashes to steam, which would blow all the fine sand out the exhaust if a dust collection system did not capture it and return it to the mix. And this is exactly where Crumb rubber has to fit in, as an added ingredient inside a system already juggling temperature, timing, and flow with almost zero tolerance for error. All this equipment exists because bitumen chemistry is deeply picky. Bitumen is the black tar-like binder left over after crude oil refining, and it only works as a proper glue for aggregate within a fairly narrow temperature window. Too cold, and the mix stops flowing before the crew can spread it. Too hot, and the bitumen starts to age prematurely, losing the flexibility that lets a road handle traffic and temperature swings without cracking. Which is why a plant like this puts so much engineering into precise temperature control, filler dosing, and mixing time. Every batch has to hit the same target properties, delivered load after load over hundreds of trucks per day. When Crumb rubber enters that same system, it needs to interact with the hot bitumen at the right temperature and mixing time to modify the binder, turning it more elastic and better at handling both heavy traffic and temperature swings. A full production day at a modern batch plant runs from before dawn to after dusk, and every 90 seconds a truck drives away loaded. Trucks queue at the gate early. Wheel loaders start filling aggregate hoppers. A conveyor lifts each portion into the drying drum, where the burner heats it to a target mix temperature. Screens sort the dried aggregate into fractions by size. Each fraction drops into its own weigh hopper, gets proportioned exactly, and dumps into the twin shaft mixer above. Liquid asphalt binder pumps in at a metered rate. The mixer combines everything for a controlled interval, usually 30 to 45 seconds, and drops the finished batch into a truck below or into a heated storage silo for later dispatch. The control room upstairs runs the whole sequence through a computer interface. Operators monitor temperatures at every stage, adjust flow rates, and watch for any deviation from the recipe. Here is the constraint most viewers never guess. Hot asphalt is only workable for about 90 to 120 minutes after it leaves the plant, which means production scheduling has to sync perfectly with the paving crew and the drive distance to the site. Modern plants push the output well past what earlier generations could manage. A global 240 unit can produce up to 240 tons per hour at 5% aggregate moisture using a multi-fuel burner that can switch between gas and diesel if a supply line goes down. The system also allows up to 25% recycled asphalt pavement in the mix. Not every road project sits next to a giant fixed plant. Some jobs happen in remote regions where dragging power lines and full infrastructure is not realistic. A mobile simplex-style plant runs on an integrated diesel engine instead of electric motors, which means the whole unit can operate anywhere the truck can reach. No high-voltage hookup, no generators, no substation permits. Electro-hydraulic hopper vibrators keep the aggregate flowing smoothly. A hydraulic filler recovery system captures 80 to 95% of the fines and returns them to the mix. The computerized control panel needs no specialized operator training, which quietly explains why paving mileage has grown faster in remote regions than most infrastructure watchers expected. Look closely at the drive system of a mobile unit and the engineering choices become obvious. The whole mixing drum runs on belts and pulleys rather than expensive gear trains, which cuts initial cost, cuts maintenance cost, and cuts downtime when something needs servicing. The control interface runs on a Siemens touchscreen panel. Operators configure aggregate rates, binder proportion, and target output on the display, then let the automation handle the rest. Bearings and drive components are heavy duty because the loads are relentless. Belts stretch under continuous tension, pulleys spin day after day, dust rides on every surface. But here is the real constraint on modern paving. The hot mix leaving these plants has to arrive at the road, get laid down, and get compacted before it cools too much to bond. That entire clock starts the moment the truck rolls out the gate. And this is where the chemistry from the plant meets the real world. A hopper full of steaming black mix, a crew with roughly 90 minutes before it stops working properly, and a road that has to end up smooth enough to drive on. The paver rolls forward slowly while a truck backs up in front and dumps hot mix into the hopper. Conveyors carry that mix rearward to twin augers that spread it evenly across the paving width. Behind the augers sits the screed, a heated floating plate that establishes the thickness and initial density of the laid mat. The angle of attack on the screed determines how thick the layer comes out, and even a fraction of an inch off target creates problems that stay in the road for years. Which is exactly where a lot of paving jobs quietly go wrong. The crew rushes, the head of material in front of the augers goes uneven, the screed cannot settle into a stable position, and the finished surface ends up with waves nobody wanted. Behind the paver comes a rolling pattern, a heavy steel wheel roller first for breakdown compaction, then a pneumatic tire roller for finishing density. Blow the compaction window while the mix is still hot enough, and the density target slips out of reach. Take that operation up to a highway project, and everything gets exponentially harder. Laying the wearing course on a section of Poland's S8 expressway means a full convoy running in continuous sequence. Dump trucks feeding a material transfer vehicle, the transfer vehicle keeping the paver hopper constantly topped up, and rollers following in a strict pattern that never lets the mat cool too far before compaction finishes. The screed here is set for full highway width, running at a controlled speed, slow enough to place the mat evenly, but fast enough to keep pace with the truck deliveries. We all know highways get resurfaced overnight for a reason. Anyone here ever gotten stuck in one of those closures and wondered what the crews were racing against? Drop your worst detour story below. Nights and weekends often get chosen for these jobs, specifically because traffic control is impossible during peak hours on a route this busy. A large commercial job, like a new fairgrounds, is where paving stops looking like one machine on a straight line and starts looking like a full production system. This project alone consumed roughly 16,200 tons of hot mix across 136 acres. Parking lots, entrance roads, RV parking, and new turn lanes on the boulevard, all coordinated so the paving train never has to sit and wait. But not every road gets built from a full hot mix train. And this is where synchronized seal work quietly does more mileage than most people realize. A synchronized chip seal unit sprays a precisely metered layer of asphalt emulsion onto the existing road, then immediately spreads aggregate on top at a matched rate, both controlled from a Siemens touchscreen. The operator sets the emulsion rate in liters per square meter, the aggregate rate in liters per square meter, and the section width. The onboard computer then calculates the truck speed automatically and executes the whole application with one press. This method is common for maintenance work, thin overlays, and preservation projects, extending the life of an existing road without tearing everything up and starting over. And now the question shifts to something most drivers never think about. How does a road handle the abuse of real traffic once the crews leave? Because the final judge of every road surface is the tire pressed against it at real speed. At Silverstone, a Formula One circuit, error tolerance drops to almost zero. The milled base was cut to within 2.5 millimeters of the design profile using GPS-controlled milling, and the finished surface hit an international roughness index of 0.26. That number is basically pool table flat over a full racing lap. Echelon paving, material transfer vehicles, and oscillating rollers all worked in sequence to hit it. Now change the constraint entirely, the runway has to reopen for aircraft in the morning. Zurich Airport renovated 61,500 square meters of a 2,500-meter runway across 44 night-only shifts, working in a hard window from about 11 p.m. to 5:30 a.m. Two 100-ton excavators and 12 articulated dump trucks removed roughly 1,000 tons of runway concrete per shift in the first hour and 45 minutes. A bulldozer spread a 280-millimeter base layer. Two pavers laid a 100-millimeter binder course. By 5:30 a.m. every morning, the whole work zone had to be broom clean and empty because aircraft started rolling at 7 a.m. sharp, which is a completely different discipline from highway paving. The schedule is fixed by an outside industry that will not wait for anyone, and every minute of overrun cancels flights and cascades through the whole airport. But after traffic load, engineers face two problems most drivers never associate with asphalt at all: noise and water. On Dutch highways, the most widely used surface is a very open asphalt concrete known as ZOAB. Its structure contains roughly 20% air voids, which does two things at once. Sound waves get absorbed into the pore network instead of bouncing off, cutting road noise noticeably, and rainwater drains straight down through the surface instead of pooling on top. Less standing water means less spray behind trucks, better visibility during storms, and shorter braking distances for everyone downstream. A similar porous system got installed at a Glasgow office parking lot recently. Around 2,000 tons of porous binder and surface course were laid to create a fast-draining lot that handles heavy rain without dumping runoff into the municipal storm system. Water disappears through the surface almost as fast as it falls. No road lasts forever. On the A20 in Rotterdam Nord, a full resurfacing campaign runs across two-week closures, replacing worn asphalt and renewing 170 expansion joints, the flexible steel and rubber gaps that let a bridge deck expand and contract with temperature. And going in even closer, the smallest repair job on the network is a pothole. The traditional method still runs the same basic sequence: cut and square the damaged area with a concrete saw, sweep and blow the debris clear, apply a tack emulsion to bond the new mix, dump hot mix from a heated tipper, spread and level it with rakes and shovels, then compact with a plate compactor. Sounds simple until the road is a busy urban street and the crew has 20 minutes before traffic backs up around them. And this is where the whole material loop finally closes. A pilot project in Richmond, Canada used 40% recycled asphalt pavement in its regular paving program. No specialized equipment required, no extra cost to the annual budget. The result? Over 2,000 tons of old road diverted from landfill and turned straight back into new road, across 800 meters of high-traffic arterial and 4,740 meters of multi-use pathway. Which raises the punchline this whole video has been building toward: a modern road is starting to look less like a permanent structure and more like a temporary material stockpile. Because the crumb rubber leaving the plant does not have to end up on a road at all. An athletic track for a French sports club uses the same end-of-life tire granulate as a base material. The existing surface gets stripped down. A layer of hot mix asphalt goes in first as a hard base. A primer gets rolled across the asphalt to help the next layer bond. Then recycled tire granules and a polymeric binder get mixed together in a paddle mixer until the material becomes uniform. A wheel loader transports the mix onto the asphalt base. A specialized paver spreads and levels it into a smooth, elastic surface. Workers hand finish the seams and edges. Line marking equipment applies preliminary and final track markings to competition standards. Same feedstock as the road surface, completely different end product. The plant sets the specification, the market decides the shape. And the same granulate can head somewhere else entirely. A masonry operation in Broome, Western Australia, now blends recycled tire crumb into concrete blocks and pavers, believed to be the first project in Australia doing this at production scale. Whole tires get shredded down to 50mm chunks, then further reduced to -8mm. Steel gets removed magnetically. The clean rubber and fiber blend then gets combined with aggregate and cracker dust before entering the block-making plant. The finished product goes onto roadside erosion protection, closing the loop right back to the road that wore the tires out in the first place. The scrap tire is one of the trickiest waste streams humans have ever created. Designed to be almost indestructible, produced by the billion, and now increasingly circling back into the roads that wore them out. Crumb rubber asphalt costs more upfront than conventional mix, sometimes 20 to 40% more per ton. Advocates point to longer service life, less cracking, and lower lifetime maintenance. Critics say the durability data is inconsistent and the extra cost never fully pays back on every road. Some states encourage or require rubber-modified asphalt in certain highway projects. If you were controlling the road budget, would you set a minimum recycled rubber requirement or let engineers choose the best mix for each project? Comment below. Appreciate you sticking around to the end. Subscribe for more deep dives into the industrial processes behind everyday materials. See ya. Take care.